Hey guys, welcome back to my YouTube channel. Today we're going to be looking at the Alex problem using osmotic pressure to find molar mass. So the osmotic pressure is the amount of pressure you have to apply to a system in order to prevent osmosis from occurring as it naturally would. It's represented by this equation right here. This is osmotic pressure, which is represented by the symbol pi. This thing is equal to the molarity times the ideal gas constant, which in this case will be 0.08206, and the temperature in Kelvin. So if you look at it, it wants the molar mass, and it actually gives the osmotic pressure to us right here. So what we have to do is, in order to find the molar mass, we need the molarity, and from there we're going to use that to find the molar mass. But first, we're going to look at this equation, and since what we want is going to be C, the molarity in this case, we're going to manipulate the equation such that it is set equal to C equals whatever. So in this case, if we look at it, all we've got to do is basically, since C is being multiplied by these two things, we'll just divide these two things, as that's the opposite function, to the other side. So essentially what it would be C is equal to osmotic pressure divided by ideal gas constant times temperature in Kelvin. So when we do that and we use what we're giving in this equation, so what's going to be on top? What's going to be on top? So we're going to set this equal to a fraction. What's going to be on top is going to be the osmotic pressure, because again, this is being multiplied, this divides, so it goes over here, so it's going to be right here, right? Right there. So in this problem, it gives us to it as 0.18, like this. And on the bottom, we're going to do the ideal gas constant, which is this, times the temperature in Kelvin. It's given to us in Celsius. So what we do is we're going to convert to Kelvin using the conversion factor, which is this, 273.15. And then now we've got our equation set up. And so if we hit enter, this gives us the molarity, right? So now that we've got the molarity, what we're going to do is we're actually going to multiply, because the molarity, so this is what the molarity means, is that it's this many moles per 1 liter, right? And so within this, we know the molarity, and we know the amount of liters given to us in milliliters, so we can use those two facts to find the number of moles. So first, we're going to multiply these two by each other, but since this is in milliliters, and this molarity is always expressed in terms of liters, what we have to do is we have to convert. So we're going to do 5 milliliters, which is this, divided by 1,000, because that's the conversion factor. And we set up the dimensional analysis, it works out and it cancels each other out. So this is how many liters we have. And then if you imagine it, it looks something like this. So it's this number right here, the 0.007 blah, 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 over 1 liter times the number of liters. So what ends up happening is that the liters cancel out because they're like diagonal from each other and whatnot. And so when you do that, I'm just going to do it here. Take this, multiply by this. And so this gives you the number of moles. And then now that you have the number of moles, what you're going to do is you're going, since molar mass is expressed in terms of grams over mole, you're going to use the fact that they give you the milligrams of it, the mass, but with the fact that you know how many moles with it to find the molar mass. So it's 216 milligrams, but obviously we don't want milligrams, we want grams, so we're going to convert to grams. And as you can see, even here, it's grams over moles, and this is grams because we just converted it, divided by number of moles, which is this we just found earlier. So this is, and then you do that, and then it gives you the answer right there. Yep, that's it.